That's fine. Okay. Yes, so today I'll be telling you about stuff that I've been mainly doing with Nika Sokolova over the past few years, though she's not in King's College anymore. She's in Daisy, so I forgot to change that. But she, anyway, when she did the work, she was at King's. Though when I did the work, I was not at ENS. But anyway. All right, so actually, we can start. Yeah, okay. We can, before I go to that slide, let's start by trying to make some connection with Parijat's talk. So Parijat was speaking about conformal field theories, and so if we to re-emphasize the point about why conformal field theories are very nice, at least from my point of view, it's that they do give you well, to re-emphasize that, probably one way to start is to think about how to solve a quantum field theory. And is the mic too close to? Okay. How to solve a quantum field theory, and one way of thinking about, or one way of saying that a quantum field theory is solved is when you manage to compute any correlation function in this quantum field theory. And conformal symmetry actually greatly simplifies this task for us. And as Parijat told us, if you have a conformal field theory, then all you need to know are the pieces of information that characterize the 2 and 3 point functions. And then if you know these pieces of information, the spectrum and the OPE coefficients, you can in principle at least compute any point function. So it kind of systematizes and also makes, in some sense, slightly easier the idea of solving a QFT if you think about CFTs. So that's the first point. And then the second point is, now suppose I do have a CFT and I want to solve it. So as Parijat told us, solving a CFT corresponds to knowing this CFT data, these 2 and 3 point functions. But what if you have some special CFT where you do know one of the two pieces of this data, right? So you let's say you have a CFT where you know the spectrum, you know the 2 point functions. Then you can ask the question, can I use the spectral knowledge which I have, combine it with some constraints, one of them coming from crossing symmetry, but also constraints coming from other properties of this particular theory, put everything together and try to obtain the second set of CFT data. So that's a question you can ask, and you can make concrete, at least that's what I want to make concrete in this talk from my perspective. I'm going to consider n equals 4 super Yang-Mills theory. So this is a 4-dimensional interacting supersymmetric conformal field theory. And so it has all of the things which are nice. In particular, it's also the first example. For example, the first example when people give when they talk about ADS-CFT. So it's holographically dual to some string theory. At the same time, n equals 4 super Yang-Mills theory also has a particular limit called the planar limit. So this is the limit when you take the rank of the gauge group to infinity, Yang-Mills coupling to 0 in such a way that you keep keep the product of theirs constant. And in this limit, there is also the emergence of an integrable structure in this theory, which actually allows you to solve the spectrum. So we do have now a CFT whose spectrum is known, and on which you can put more constraints, i.e. Either from crossing symmetry or from string theory via holography. So now, maybe keep this here. So now we can actually see if what I said in the motivation can be taken to some kind of fruition, like you take the spectral information, plug it into these constraints and see what you can extract about 3 point functions or OPE coefficients.
So when you say the spectrum is known, you mean the energy eigenvalues of the excitations?
Yes, yes.
Not the matrix elements between excited states.
So, yes. The energy. So when I say the spectrum is known, what I mean is that the eigenvalues of the dilatation operator are known. Yeah.
Because if you also knew the matrix elements, you would have calculated the open.
Of course. Yeah. So there is, okay, good. So there is so that I will not explain in details at all about the technology used to solve the spectrum, but the technology used to solve the spectrum comes under the name of, at least the one which we use comes under the name of quantum spectral curve. And using this method, basically you solve some auxiliary Riemann-Hilbert problem for some Q functions, and then you take those Q functions and extract the spectral information from them. But now this is a subject of ongoing research, but you can indeed, as the Q functions in principle are strong candidates to be eigenvectors of the dilatation operator. So indeed there is a program of research which is trying to understand if it is possible to take inner products of these Q functions with some measures to extract OP coefficients. So there is varying degrees of success. It's an ongoing research field. People are working on it. So indeed, yeah, that's it's true that in some sense, once you have integrability, you probably don't need anything else. But okay, at the current state, the hybrid approaches are important. So at least in the future, when people figure out how to do that, then there are like checks and stuff like that that you can do with this. But for now, this is predictive. Okay. So yeah, so to make concrete a bit more what I was saying till now. So super Yang-Mills theory, as I said, it's a 4-dimensional interacting quantum field theory. You have the Yang-Mills coupling, and you have the rank of the gauge group, the number of colors. So you take the planar limit. So you take Yang-Mills coupling to 0. You take the number of colors to infinity, in such a way that this thing lambda, the Tuft coupling, is kept fixed. Now again, as there was some discussion in the previous talk, when you take large n, what happens is you have factorization, and as a result, all you need to consider are single trace operators, where the trace is over the gauge group. So all you need to consider are single trace operators. And these single trace operators look like this. So they are a trace of L things, and these L things are made out of your favorite number of covariant derivatives acting on the fields in the n equals 4 super Yang-Mills Lagrangian. Okay, so just take a bunch of fields, act on them with as many covariant derivatives or no covariant derivatives, take care of them, and that defines. These are bases, let's say, for your single trace states. Right, so this is the basis for your single trace states, and however, you would like to have a nice way of labeling them. So the labels, the states in this theory, of course, are labeled by the charges of their charges under the bosonic symmetries of n equals 4 super Yang-Mills, which is SO42 times SO6. SO42 is the 4-dimensional conformal group, and SO6 is the R symmetry group. So it's you can think about it as some global symmetry group. It's a consequence of super conformal symmetry. But anyway, so these are so SO4, 2 times SO6 is the bosonic symmetries. This is the bosonic symmetry of this theory, and therefore unique labels of a state. Therefore, to have a unit to uniquely identify a state, you need 6 labels. You have Q1, P, Q2, which are the Dynkin labels of your SO6, and then you have delta L1 and L2, which characterize the SO4, 2. So L1, L2 are spins, delta is the dimension, and Q1, P, Q2 are Q1, P, Q2 are Dynkin labels of SO6. Now, out of these 6 labels, 5 of them are always integers or half integers, but the 6th one, which is the dimension, so which is the eigenvalue under scaling, right? This in general can be a non-trivial function of the Tuft coupling. So it's in general some function undetermined as of now function of the Tuft coupling. But the point is that so there was a lot of work. So okay, maybe I can, since we have time, maybe I can say a few more words on this. So the story started, well, the story in the n equals 4 version started maybe 25 years ago now, by a paper written by Minahan and Zarembo, where basically what they showed was that at one loop, the mixing matrix of a particular sector of states. So you take a trace of L things, but these L things, you just allow them to be scalars, right? So you can just have trace of L scalars. There are 6 scalars because the scalars transform in the fundamental of SO6. So in principle, there are 6 to the power L possible length L operators that you can make with 6 scalars. And in principle, and if you want to diagonalize the dilatation operator at one loop, then basically you should be able to compute a 6 to the power L times 6 to the power L mixing matrix of all possible 2-point functions. And then you diagonalize this mixing matrix. And when you diagonalize the mixing matrix, the eigenvectors will give you those linear combination out of these 6 to the L operators, which are your good conformal operators. And the eigenvalues will give you your scaling dimensions. This is just standard QFT problem, but what Minahan and Zarembo understood was that at one loop, this mixing matrix is just the Hamiltonian of a Heisenberg XXX spin chain with SO6 symmetry. So therefore, this thing is integrable. You can apply Bethe-Ansatz, blah, blah, blah. And that was the start of integrability. Of course, it turns out that integrability is preserved in all possible ways, in all possible generalizations of this. Yes?
So, you said the Yamness was in 4 dimensions, right? How did they reduce it to a spin chain in 1 dimension?
Right. So, no. So you literally write down the mixing matrix, and the mixing matrix can just be mapped to the spin chain. Yeah, exactly. But indeed, so now there are multiple ways in which you generalize this. First thing is, I said only SO6, right? So I only allowed scalars, but I can put all of these things. It turns out that at one loop you can put anything, and it's still integrable. The next question that you can say is, can you go to multiple loops? At higher loops, it turns out it is still integrable, and I think up to 2 or 3 loops, there is also a map, at least in some sectors, back to spin chain Hamiltonians. The difference is that as you go to higher loops, the interactions are not nearest neighbor anymore. So at one loop, the interaction is nearest neighbor, but as you go to higher loops, the interaction become less next to nearest neighbor, next to nearest neighbor, like this. But still, you still get integrable Hamiltonians. Of course, for those people familiar with this, you will understand that if I have a spin chain of length L and I go to L loops, then I'll get a spin chain interaction that wraps around. So these are, for example, these were important technical problems that were there, but also people understood how to deal with them. Independently, if you take the large L limit, you take L going to infinity, then this is the classical limit. And in the large L limit, you can also consider using holography, the string sigma model in the classical limit, the dual string sigma model in the classical limit. And that was also shown to be classically integrable because you can construct a flat connection and all of these things. So in general, in all possible generalizations, the integrability persisted. There was a lot of works which showed all of this.
So how is the length of the spin chain related to this?
So you mean the classical limit? Well, it's the, what's it called? So when you, it's, if you have any quantum system and you take the charges to be very large, you are approaching the classical limit, right? It's the h bar goes to 0 limit. So it's the same analogous.
The problem that you mentioned.
Yes.
So that depends on the length of the spin chain.
Indeed. So at one loop we are lucky. So you just have a length L operator, and you just get yes, indeed. The size of the mixing matrix depends on the size of the spin chain. However, indeed, there is a subtlety here which I didn't mention, but I can say now since you have asked, which is I'm assuming that the length doesn't change, that there is no interaction which can change length. That's true for SO6 if I only have scalars, but if I have another sector called SU2/3, for example, I can, as Antonio recalls from last week when we discussed, but you can exchange 2 fermions for 3 scalars, and that will change the length of your spin chain. So at some point this sector becomes important, so you have to do some other thing. You can't always say that you'll have some fixed length spin chain. So there are subtleties like this, but these are, I think already 20 years ago people understood how to deal with this. Anyway, so all of this culminated in the writing down of the quantum spectral curve. which is basically a non-perturbative realization of this integrable structure of planar n equals 4 super Yang-Mills. I don't think I have anything more to say about it except just show you, just say that using the quantum spectral curve, it's possible to actually compute the dilatation operator, and I'll just show you the spectrum that we generated using that, and that's here. So 2 years ago, along with, so Gromov was one of the inventors of the quantum spectral curve, and along with him, we basically just understood how to implement this, like this. Essentially what the quantum spectral curve is that you take your spectral problem and you associate it with an auxiliary Riemann-Hilbert problem that you need to solve. But you actually need to solve that Riemann-Hilbert problem, and there were some technical issues there, which we managed to understand and make the implementation make the implementation possible. And once we did that, we were able to obtain the spectrum of this theory, and this is what it is. So these are all states with dimensions 6 or less. So there are 219 states which bear dimension 6 or less in planar Yang-Mills, super Yang-Mills. And so this is just a plot of their dimensions. So we can go.
Sorry, so you were saying this map, like quantitatively loop by loop.
Yes.
But this is non-perturbative.
This is non-perturbative. Yeah.
So when you go to the, like, what's the proposal at the non-perturbative level? Like, there is all-to-all interaction in the spin chains?
So you don't have a spin chain picture in the. Yeah. Okay. So, sorry. There is. Yeah. Okay. There is some kind of spin chain motivation in the non-perturbative statement. So in the non-perturbative statement, so let me see what's the easiest way of saying this. Maybe I can write something on the board as well. One sec. I just want to see what's the easiest way to explain this. Okay. So right. Is this board fine?
Closer to the screen.
Sure. Where should I draw the line?
Actually, it's best if you are on this side.
But okay,
and not too far.
not too far away. Okay. So where should I draw the line? Here?
I mean, you can use the entire board.
Yeah.
This depends on.
Okay. Anyway, I don't know how much I'm going to write. So okay. So let's consider just the SU2 sector. Okay. So this SU2 sector it's an even smaller sector. So you have over here you have basically two operators x, which is defined as phi1 plus I phi2, let's say, which is some complex scalar in your theory, and you have, I don't want y, I want z. I mean, it doesn't matter, but so you have two complex scalars out of three complex scalars, and SU2 sector just tells you that you want to compute operators like this. Okay, just some trace with z's and x's in it. Now what Minahan and Zarembo tell you is that this thing you can map to some SU2 Heisenberg spin chain like this. Okay, with the Hamiltonian, can I write here? With the Hamiltonian sum over sides, so some length L, so I equals 1 to L, identity minus permutation. So this is just a standard Heisenberg spin chain with some Hamiltonian. And so what Minahan and Zarembo tell you is that the states map like this, and the mixing matrix maps to this. So what you want to do is diagonalize this Hamiltonian. Now, if you want to diagonalize this Hamiltonian, you can easily see that the ground state is all spins down. There's no problem, right? Because all spins down, identity and permutation cancel each other, so that's fine. But excited states take the form of what are known as magnons, where what you do is so what you do is you just have one spin flipped. I mean, this is a one magnon state. So in this state, I flip one spin, and then I put some phase in front of it, and then I sum over the chain. And why I am doing that is because, let's just back up. So the ground state is all spins down, but now if I flip one spin, plug it here, what the Hamiltonian will do is that the permutation operator will move it one step to the left and one step to the right. So then naturally you understand that the eigenstate should be spins which are going around. So this is some concept, this is that concept basically where you have some flipped spin going around the spin chain with some momentum P1. So this actually can't be an eigenstate, but eigenstates are built out of magnons like this. And then this implies.
Yes, maybe it's better to now shift to that side.
Good, okay.
You do that.
Yeah, that's fine. Here?
Yes.
Okay. So that then implies what's called the Bethe-Ansatz equations. Very simply, what the Bethe-Ansatz equations just mean is that if you take a magnon, take it around the chain, it will interact with everything, but it comes back to itself, right? So that thing you can write down. You can write down some Bethe-Ansatz equation for. So you take an M magnon state. So that I wrote a one magnon state. You can write a state with M magnons. So you put so many phase factors, flip so many M phase factors, flip M spins, and allow all of them to go around. So you have an M magnon state, and the Bethe-Ansatz equation just tells you is if you take one of the magnons, scatter them through the other magnons, and come back, you should do nothing. And that's encapsulated into the Bethe-Ansatz equations, and solving them, you get your magnon momenta. And then once you know the magnon momenta, you go back there, you plug it in there, you get your eigenstate, and then you also get your eigenvalue. So if you know the magnon momenta, there is some formula which translates that into the energy. So there is, you can go from magnon momenta to Bethe roots. There's just some transformation that takes you from this to that. And the point is, if you know the Bethe roots which solve the Bethe-Ansatz equation, you know magnon momenta, and then from magnon momenta you know the eigenvectors, and you know the eigenvalues from, I think this is the, I'm writing this from memory, so I think this is the formula that gives you the energy, so it gives you the eigenvalues. Now the point is that I can take all of the information. So what I'm trying to say is all the physical information is in the magnon momenta, which you got from Bethe-Ansatz equation. So what I can do is I can take all the Bethe roots, put them into a polynomial, and store them here. Call it a Baxter polynomial, just to keep track of this information. At this point, I'll go back to what I was saying there and say that I said that all spins up is a ground state. But of course, I could have said all spins down is also a ground state, right? It's also a ground state. But then a state with M magnons in a spin up vacuum is the same as L minus M magnons in a spin down vacuum, right? If I see that from a different perspective. But these are equivalent descriptions of the same system. So essentially, there is another set of Bethe roots which correspond to this second system, which is completely equivalent to the first system, and you can put that into a second Baxter polynomial. And now these two Baxter polynomials are essentially dual to each other, but they also are solutions to a finite difference equation called the Baxter's TQ relation that characterizes this integrable model. Okay, so this entire story is for just SU2 at one loop, but philosophically the QSC is the same thing for PSU2, 2/4 non-perturbatively. So let me explain what I mean by that. So in this case, there are two Q polynomials. There are two more trivial. There are two more. Just to complete the system, there's also a trivial Q empty set and another Q function called U to the L. So U to the L is one. So these are the two important Q functions, and then there are two just to complete the set. So basically, there are 2 to the power rank of SU2 minus 1, or that's right, no? Maybe not minus 1, but anyway, there are plus 1, that's fine, yeah. So there are 2 to the power rank of the group plus 1 number of Q functions which characterize a spin chain, okay? So in case of SU2, which is what I was talking about, there are just 4, 2 of them are trivial and 2 of them are non-trivial. Now you can generalize this entire statement to PSU2, 2/4 for full super Yang mills. That's what the quantum spectral curve is basically. So now you have, instead of so for this, so now instead if I consider PSU2, 2/4 spin chain, now this thing has rank 7. So there are 2 to the power 7 plus 1 equal to 256 Q functions. And all of these 256 Q functions are related to each other via various dualities. Similar, very, very like conceptually exactly the same as what I explained. The only thing is, of course, that this is a supersymmetric spin chain, so there is some more subtleties due to that, but that's what they are. They're just subtleties. So so the quantum spectral curve, essentially one part of it is just this. It is a spin chain for PSU2, 2/4. However, there is a second thing. So all of this, what I told you till now about SU2 was at one loop, was at the mixing matrix for one loop. But I'm trying to make a non-perturbative statement. So if I want to make non-perturbative statement, then I need to insert the definition of coupling somewhere into this story, and basically when you do that, you will see that you cannot have polynomials anymore, but you have to have more complicated functions where there is some coupling dependence. And to see how that comes about, yeah, I'm doing fine for time, so I think I can try to explain something about that, but slightly more vaguely. But if you take this classical limit, you take the length of the spin chain now to go to infinity. At this, when you do that, basically your system should be described by a sigma model. So you do the classical limit and then you look at the holographic dual. When you do that, you will see that you're actually studying the classical sigma model of strings, classical string sigma model on R times S3. Okay.
One question: usually when you take the classical limit spin models, you said that you're considering a spin half quantum chain, right?
Yeah.
Usually you take that spin quantum number to infinity.
Okay.
Yeah, because you can still have a length L Heisenberg chain which is as quantum as it can be for whatever L you choose, right? So I guess
Yeah, so you also scale the Bethe roots in some sense. So you don't just scale the length, you also scale the Bethe roots so the Bethe root ui goes to L times some xi. So that's the limit that you take. You make the Bethe roots also really large, and you also make the spin chain very large. That's the limit that I speak about. Is that, yeah.
If you want, there is indeed a quantum number like that in the line, which is this SO6 global symmetry. Those quantum numbers will be large, even though they are spin on half.
Yes. Yeah. Indeed.
ultimately you want some commutative relations to be trivial.
Yeah. Indeed. Exactly. Yeah. Thanks, Antonio. And right. And those quantum numbers being large, that comes from taking the Bethe roots to be big guys. Maybe not. No. Yeah. Okay. If you take it just comes from having many Bethe roots, not large ones. But yeah. Indeed. Right. So then to see how the coupling dependence comes in, you have to look at the sigma model picture. So you have some sigma model on R times S3, and so the integrable structure of the sigma model basically will tell you. Okay, I think it's a bit hard to explain in words, but the point is that you have to introduce information about the coupling constant into this picture somehow if you want to make it non-perturbative. So basically you have the same structure as I explained here, but your Q functions, in this case they were just polynomials. they become modified and they get some coupling dependence inside them. And that's what is the quantospectral curve. So the quantospectral curve is basically a Riemann-Hilbert problem on these Q functions that you solve in order, to obtain expressions for the Q functions. And then, as you can see there, if I want to extract the charge of the state, I just need to take the large U asymptotic. So just take the large U asymptotic of the Q function and extract the charge.
So one thing that remains a bit mysterious is that at one loop you started from a Hamiltonian, you derive some excitations, you write some Bethe-Ansatz equations.
Yes.
So that's fine. Non-perturbatively, it looks like you have to guess the problem also, not just or there is some concrete path to write down the correct Bethe-Ansatz-like set of equations. You see the question?
So I think, yes, I see the question, and I think indeed. So there was some, so Bizert and others, they worked on this, and they basically understood a way to bypass this Hamiltonian and directly go to the Bethe-Ansatz equation. So you specify charges and then you get Bethe-Ansatz equations. Remove the Hamiltonian. So there is a way to do that. Yeah, indeed, it's not. Indeed, it's if you have to go through the Hamiltonian, it's not trivial.
So somehow you're saying that these charges, which are the conserved quantities of the integral theory, they keep getting dressed in some way as you change your lambda. Is that
Just the dimension keeps changing, right? Just the scaling dimension. But sorry, Antonio. One sec, I'll come back to you. But actually, no. You can see it right here. So essentially, once you realize that you have these two Q functions, and then you realize that these Q functions are solutions to some Baxter-TQ relation, now you know. Now you can actually forget about the Bethe-Ansatz completely, because you just have your Baxter equation. You have your Q function. You have your Baxter polynomials, which you know should have this particular asymptotic.
That sounds like a guess, right? It didn't start from the dilatation operator. You kind of guess that you see what I'm saying? You're not deriving that
Yeah. Okay. Sure. Okay. Yeah. So that's fair. Yeah, that's fair. Yeah, indeed. Okay. So for that, some work is needed. Indeed. So to what I was saying, the dimension will change for the Tufte. The other charges don't change. So, but I mean, the way you think about it is you fix your dimension and then you solve everything. So there will be some value of the dimension. Then you change the dimension slightly and then solve everything. I mean, change the coupling slightly and you solve it. Okay. So right.
Instead of just saying it involves these x's and z's, which are some fields in this Lagrange, can you define it as like a set of operators annihilated by some combination of supercharges?
Some combination of. I'm sure it's possible to do that. Yeah. Yeah, I'm sure that's possible because. Yeah.
So defining the SU2 sector, can you get an algebraic definition, the kernel of some combination of integers?
Yes. I don't know it out of the top of my head right now, but indeed you can define it, I think. Okay, good. Hopefully this discussion demystified the QSC a bit. Anyhow, so we understood how to numerically solve this Riemann-Hilbert problem. Well, people already understood it before us. We just understood how to cure some subtleties. And our Hungarian collaborator, Hegedus, managed to code everything in C++. And so it's available open access. You can download it and run this stuff, reproduce this plot on your own laptop as well, if you so desire. All right. Right. Okay. So now, well, this is So basically, this is kind of the background which I wanted to give. So now we can move on to actually addressing the question which I started off with. Which is, can I now use this information add to it some constraints coming from wherever, in particular crossing and holography, and try to extract beyond the spectral information. So in order to do that, first I wanted to show you some more numerical results. So basically for some subsector of states which are just easier to deal with numerically, you can push this stuff even further, and you can go to really high values of the 't Hooft coupling. And when you do that, you actually see some stuff which is emerging. So from ADS CFT, you know, or you expect at least, well, I think we can say we know now that single trace operators are dual to short massive strings in ADS. And the spectrum of short massive strings in ADS, if you look at, I didn't cite them, but the Gupser, Klebanov, Polyakov, they told us that the spectrum of short massive string should go like that, where you have 2 times square root of some integer times lambda to the 1/4. So that's how you expect. That's how you expect the spectrum of short massive strings in the flat space limit of ADS to look like from ADS CFT, and from ADS CFT. These should be what the dimension of the single trace operators go to at strong coupling, and indeed that's what we see. So you can plot some of these states like this, and then then you can just make some fit, and you will see that this thing goes as 2 times square root of 1 lambda to the 1/4. This band at leading order goes like 2 square root of 2 lambda to the 1/4. Next one goes 2 square root of 3 lambda to the 1/4. So first of all, that's the first thing that emerges. The next thing that emerges is that we are going to the flat space limit. So we expect some Kaluza client towers to emerge, right? This SO5, this SO6 these SO6 representations should condense into Kaluza client towers of SO5, and we see that as well. So over here, for example, so this is the Konishi operator, this guy here. This is the Konishi operator, which has R charge 0, 0, 0. And essentially here we see that at every value of the dimension, at every value of the bare dimension, there is one operator with slightly higher R charge than the Konishi operator, which at strong coupling comes, and then it sits on the Kaluza client tower above the Konishi operator. So we can also start seeing this organization of the spectrum into Kaluza client towers. Both of these things expected from ADS CFT. So it's very nice to actually to see that happen. So now that we've seen it happen, how do we use that? So let's, yes, Andrew.
Yes, I'm a bit unrelated, but this is such a nice plot. So, since you have this finite coupling and in fact very strong coupling things, can you investigate properties of perturbation theory around zero and infinity? And what I have in mind in particular is at zero coupling, explained that there's some finite radius of convergence.
Yes,
right?
yes.
Is there something special going on in this plot when you reach the finite radius of convergence? Or?
So the finite radius of convergence should be, so actually it should be at, well, it should be at G equals 0.25, where G is square root of lambda over 4 pi, so whatever, it's somewhere
so
here.
Is it when the first states cross or something? Or
No,
it's
no.
somewhere special?
So it's I think, okay, let me give you my first reaction would be, I think states cross already before the radius of convergence is reached. This is what I think, but this is something I need to investigate. This is something we can check. We have the data, so we can just check it. But I suspect they should cross already before that. So sorry, so you were saying what?
Do you see something special when you look at the spectrum at the point where the radius of convergence is?
Yeah, so no, I mean we haven't checked, so it's something we should do indeed.
But the curves are just smooth, so no value feels like there's something going wrong. It's continuity.
No. No, but that you will never see because of integrability, right? Like, because, I mean, what it means, the fact that crossings don't cause any problems is a result of integrability anyway. So.
Roughly, what is this finite radius of convergence?
Somewhere here. So that's why it looks like, so the perturbative series will converge until there, basically. Okay, right. So now that we have this information, how do we actually use it? So let's analyze a bit the spectrum at strong coupling. So as I said, we need to reproduce the scaling dimension of massive strings. So an ansatz for that is like this. So you have 2 times square root delta lambda to the 1/4, and then you should have some constant term, and then essentially a series in powers of 1 over square root of delta. So that's an ansatz. So what we just take this thing, and we fit our data and try to extract these coefficients, these d coefficients. The first surprising thing that we realized was that d naught, so the constant equals -2, is universal. So we really saw that for all of the states that we considered, we see the strong coupling behavior with some string state, but then we see that they're all shifted by the same amount. The constant shift is the same, and we have some kind of explanation for it. So the way the explanation for it is the following. We say that instead of looking at the scaling dimension, what you should look at from ADS CFT point of view is actually the quadratic Casimir eigenvalue, right? Because this is the thing that actually maps to the mass square in the string. And the quadratic Casimir eigenvalue is this for PSU 2,2/4. If you write down quadratic Casimir, you get this. And here you can see that it's got this delta plus 2 square. So now, if we demand that the quadratic Casimir eigenvalue has a regular expansion in powers of 1 over square root of lambda, that can only happen if you have this ansatz for delta with d naught equals -2. So this is some kind of heuristic argument that we give to kind of try to explain why we get this. But this is just a heuristic argument which we thought intuitively it makes sense. But nevertheless, one of the lessons that we took from this analysis was that it's more important to focus on the dimension, to focus on the eigenvalue of the quadratic Casimir of PSU 2,2/4 rather than the dimension itself. So actually, hereafter, I will talk about, when I talk about dimension, the dimension will actually not be characterized by delta and d's anymore, it will be characterized by j's, okay, which are just, it contains the same exactly the same information from the spectrum point of view, right? But it also has some extra information from here, which we will see becomes, turns out to look quite interesting. So indeed, so at strong coupling, the eigenvalue of the quadratic Casimir just goes as 2 times some number times square root of delta plus j1, some correction, plus j2 over square root of lambda, blah, blah, blah. So in other words, instead of the dimension at strong coupling, I can just think about this little delta which gives you the string mass level and this list of j's. Okay, so whenever I say from now on, this is what we will think about. We will forget about this non-perturbative picture, and we will just take these j's and delta. And the reason we do that is because, again, going back to my initial motivation, what I want to do is I want to make use of this, make use of some results from holography to try to extract more information. So I want to focus on strong coupling. Okay, right. So that's good. The second thing. Okay, I need feedback on this slide later on whether it's a useful way of explaining things or not. But I will show you what's going on here. So I made a statement before that the spectrum organizes itself into Kaluza-Klein towers at strong coupling, and indeed we see this. But what we wanted to do was, when we generated all of this data, we really wanted, just to do a basic zeroth order check. We wanted to just match the counting of states that you get on the string side with the field theory side. Like, are we seeing all of the string states, right? So at weak coupling in the field theory on the weak coupling super Yang-Mills side, this is not a problem because already the perturbative solution of the quantum spectral curve that we used to initialize our numerics was already complete. It was proven by the people by Volin and Marbo, who actually developed the solution as well. So that was fine. At strong coupling, the counting needed to match. We needed to see that we are producing all of the states which are expected. Now, if you try to count these massive strings at strong coupling, what you will end up doing is you will end up so what the procedure for counting strings of strong coupling and was done by Fernando Alday and Tobias Hansen, João Silva a few years ago, and the procedure that they used was the following. What they did was they were counting representations of SO9, which is the massive little group of R1, 9. Then because they wanted to count massive strings in 10D. Then what they did, they took these representations of SO9, they took their counting, and then they branched this SO6 representations into SO4 times SO5, because they are keeping in mind that they are going from ADS5 times S5 in the flat space limit. So you branch the SO9 into SO4 times SO5. And then what you do is for each of your SO5 representations, you condense that into a Kaluza client tower. You allow you do a compactification of that space, and then what you output is for a given value of the string mass level, you have some counting of Kaluza client towers that you can get. Good, that's what they provided us, and what we did was we were producing data, and we wanted to see if we can map our data which we get to the Kaluza client tower counting done by Alday and friends. And basically the reason for saying all of this is just to say that we need to understand how to sort states into Kaluza client towers. So this is an example of some of the data analysis that we did. So okay, so here we have various, I mean this is the same table of states just written 4 times. So this is a table of states with 5 quantum numbers L1, L2, Q1, P, Q2 of each state given here. They're all states with string mass level 2, and all of these, and this is the numerical fit for the sub leading dimension at strong coupling. So you can see it looks pretty close to rational numbers. So this is a base, based on this is a guess for D1, the dimension at strong coupling, the sub leading dimension coefficient at strong coupling. So based on this is a guess for D1, and then this is, so once you know D1, you just plug it into this Casimir formula and you get J1 instead, right? So these are, I mean, so this is just output of the fit, guess for that written in 2 different ways. If you just look at the D1s, they are just all kinds of numbers basically. I mean, there's a lot of multiplicity in the numbers, so it's not very clear which D1 corresponds to which state. Is there some relation between the D1 of a state and the R charge of a state? Because that's what you would want to see if you want to say that 2 states are in the same Kaluza client tower. With D1s, actually it's not that clear, but if you look at J1s instead, then you immediately start seeing some patterns. So firstly, you see that there are 3 states here which differ just by R charge, but the value of their J1 is the same. And we see this happening many times. Actually, in this case, there are only 2 values of R charge that we see. It's only 2 or 14. But regardless, you can continuously see that now there's another. So the blue guy. So then we claim that the green states are 1 tower. Then we look at the blue ones. Sorry, this is not blue. This is yellow. We look at the yellow ones. Again, we see that there are states with continuously increasing R charge, but they have the same value of quadratic Casimir. So then we say that okay, these are also in 1 Kaluza client tower. And then lastly, we see also here there are some blue states with some funky representations of the R symmetry group, which also fall neatly into Kaluza client towers. So then we do this Brazilian flag the yellow ones. So so the yellow ones. So there is basically, so there is 0, 2, so 0, 1, 2, 3 here. So it's 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0. And then there's also 0, so then there's also 2, 0, 2, 0, 2. So, okay, basically there are states with R charge 0, 0, 0, 0, 1, 0, 0, 2 states with 0, 2, 0, 1 with 0, 3, 0, 1 with 0, 4, 0. So one of them forms 1 Kaluza client tower. Another one is a lonely Kaluza client tower which starts at 0, 2, 0, again expected from counting. and then there's a third Kaluza-Klein tower which starts from 202. So 202, then if we initialize more states, then we will find 212, 222, 232, for example. Yeah. So, okay, the takeaway from all of this was that we understood, again, this is a conjecture that we made, was that the value of the quadratic Casimir eigenvalue characterizes the Kaluza-Klein tower that we are dealing with. So, in other words, all states in a given Kaluza-Klein tower will have the same value of the subleading quadratic Casimir. That's something that we noticed for like some cases, and then we kind of, well, I mean, we noticed it for all of the examples that we studied. So all of these 219 states we were able to classify into Kaluza-Klein towers using this observation. We were able to match the counting that Aldai and friends did, and so now we then promoted that classifier to conjecture, and then we said, okay, all states in the Kaluza-Klein tower will have same value of J1. And what that lets you do is just invert this relation and say that now if I know the value of J1 for the state at the bottom of a tower, then I can predict the value of D1, the value of a dimension for any state at any value of the R charge. So yeah, so that's a prediction that we made. Anyway, this is more information to tell you that J1 is important from our eyes.
So one thing that's incredibly impressive about this is the amount of nines and zeros that you get, which means that
Amount of nines and zeros, yeah, indeed.
Number of decimal places.
Yeah, yeah.
Fit of the subleading.
Yes.
Does this suggest that if you subtract out these terms, you can still fit the subleading curve? I mean, large coupling expansion, there's probably some expectations for what type of numbers appear. Like
Yeah.
some pies will appear.
Yeah, so no, at next order you expect to get something rational number times zeta 3 plus another rational number.
And can you not measure those numerically?
You can to some extent. So you have to assume this, probably this many zeros is not enough. You probably need double the number of zeros, but then you can. But actually right now, after our paper came out, Gromov and other collaborators managed to write an even more strong coupling optimized numerical procedure, which you can use to generate a lot of zeros here. And then indeed using that method, you should, yeah, I mean, it's possible. But the answer to your question is yes. We did it for some states here as well, because as we were finishing this paper, Fernando and Tobias were finishing their paper where they had some predictions for D2 independently from Bootstrap, and we kind of matched that. So we did, it is possible, we have done it. Yeah,
D2
is the next one. Okay, so now we get to 3-point functions, and I have like half an hour left, which is good. Okay, so what are the kind of 3-point functions we want to compute? We want to compute the 3-point functions of 2 massless strings with 1 massive string. Okay, in particular, the massless strings could be either gravitons or their KK modes, and then you have 1 massive string exchanged. A CFT observable which produces this 3-point function is this sort of correlator in super Yang-Mills. So you consider a 4-point function of O2, O2, O2 plus P, O2 plus P, where OK is a Lorentz scalar which transforms as symmetric traceless tensor of rank K in SO6. Okay, so these are the chiral primaries of n equals 4 super Yang-Mills. So we want to consider such 4-point functions. If you do an OPE of O2 times O2 plus P, then you will exchange many things, but you will also exchange massive strings. The massive strings that you exchange will have quantum numbers. They will have delta LL 0P0. L is even, I should say. Or in the language which I like to use, you will have a set little delta J1, J2, blah, 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 LL 0P0, where P is the R charge of the exchange state. So in particular, if I have O2, 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 then I'll just have a state which is R which is not charged under R symmetry. Right. So these are the states which are exchanged, and these exchange state are associated with the T-channel OP coefficient, which is the positive one. So if you have O2, O2, OP, OP, then the positive OP coefficient is the T-channel one, which is this thing. So it's some very ugly normalization factor, important but ugly normalization factor, and then times something that you can do an asymptotic expansion of about. So from now on, the characters in the rest of the story are going to be delta j's, which represent the dimensions, and these f's, which represent the OP coefficients. So the game we will play over the next half an hour is just to understand if there are some constraints where I supply information about deltas and j's, and I can extract f's. Okay, that's the game that we're going to play. So how do we get constraints? So to get constraints, before we get constraints, let me talk a bit more about the spectrum of massive strings in the flat space limit. So as we go to strong coupling, we are probing flat space limit. Massive strings organize themselves into Regge trajectories, and they look like this. So you can make a Chew-Froutschi plot like this, where you have mass levels like this and spins going up, and these states, this state, so the states which have the least value of spin for a given mass level, they form the leading Regge trajectory, and then you have subleading Regge trajectories as well. For a given value of delta and L, so for a given value of mass level and spin, generically there are multiple states. You don't always have a single state, which is again similar to what Parijat was telling us about, which is even after you fix all quantum numbers, you have some mixing, right? So it's similar sort of thing that you see here. Generically, if you fix mass level and spin, you will have more than one state with same, all charges same, including mass level and spin, except for the leading Regge trajectory, which is non-degenerate. So the leading Regge trajectory is non-degenerate. Subleading Regge trajectories, they do have degeneracies. Okay, so that's something important to keep in mind, because in the future, when we are going to, well, in the future meaning in the near future, when we are going to solve these equations, we are going to write down equations as functions of Regge trajectories, and therefore we have to keep in mind that if we are not on the leading Regge trajectory, there is a multiplicity that we need to solve for. There is a mixing problem that we need to solve. All right. So now let's see actually how to get some constraints. So to get the constraints, we consult our friends at Oxford, who have been, well, now not everyone there is in Oxford, but started, let's say, at Oxford, who were computing these systematic curvature corrections to the flat space Virasoro-Shapiro amplitude. So that you take a 4 graviton amplitude, a tree level 4 graviton amplitude in flat space, and then you and then they were systematically computing ADS curvature corrections to this. Right. Now the point is the following. The point is that every time you find a new curvature correction, to the flat space amplitude, you get some constraints on the CFT data exchanged in the dual 4-point function. So that's the source of our constraints. So until now, for various choices of p, so for p is equal to 0, there are two curvature corrections computed. So we have a bit more constraints, and then for p not equal to 0, there's one curvature correction computed. But nevertheless, the point is that every time you compute a curvature correction, you have some constraints. And now what we want to do is we want to take those constraints which come from holography, and those constraints are on f's and j's. We know j's, so input the j's and try to extract f's. Okay, this is the game that we will play.
So these are the constraints on the invariant?
Yes, indeed. So you get some So you translate that back into indeed. Okay, so this is the strategy, what I explained in words. It's here. So you start with some, so this is what I explained in the previous slide, and the point is the following. So you start, so we're just going to focus on F0, which is the tree level, which is like the leading term in this 3-point functions, right? We just want to focus on F0, so we start with constraints on F0. Already from the flat space Virasoro-Shapiro amplitude, you already know some constraint on just what F should be. Obviously, the sum here is over all states. So this, for every value of delta and L, you will have some multiplicity of states, and this constraint that you get is a sum over all states with that given value of delta and L. From the first correction, you get a constraint like this, which is on F0 times J1. So that means F0 J1 comma M, and you sum over M for all states with a given value of mass level and spin. And then for the 1 over R to the power 4 correction, you get a constraint of on F0 J1 square. Okay. So we take these 3 constraints and then we input J, and then we see what we get.
I had something very naive to ask.
Sure.
So if you started off with the flat space
Yeah.
version out there, what are you saying about the CFT? Are you saying, anything about it at all?
So
not including, I understand corrections will give you something
Yeah.
on the dual CFT side.
Yeah.
But the leading order piece, there is no CFT, right? It's flat space.
Yeah. Okay. Yeah. Sure. Okay.
Yeah. So what's the
So even that is actually giving you some information on the OP coefficients of the CFT in the extreme strong coupling limit. So indeed, it is just flat space, but it gives you some information about the OP coefficients in at extremely flat, at extreme coupling.
If you go back to Julius's plot, in the extreme limit, things accumulate to this trajectory. They are all very dense, but there is some degeneracy, and you can think that that's the CFTs. All the dimensions are strictly infinity, but
symmetries don't match, right? Symmetries don't match.
it's an order of limits issues. It's large radius.
Well, okay, but you should also not say that I'm in flat space. I'm very close to flat space. So,
You're
yeah.
very large.
Yeah.
And you're just looking at.
Yeah. That's probably the correct way of thinking about it, because also then there is some sense of this. There is some splitting indeed. Because indeed, you're right. If I just have flat space, I'd maybe even saying that there is no the Reggie trajectory, the tube plot is the tube plot, and that's it, right? So now I'm putting some fine structure there, indeed, and so that. All right, thank you, Antonio, as well. Right, so this is the strategy, and right. So now let me explain the results of what we did. So first up, as I said, when you just consider O2 plus P, then there's only one curvature correction available. So we have a more restricted system, less constrained system in some sense. But okay, anyway, let me explain what we did there. So the data that we have from integrability gives us the knowledge of all j's inside this triangle. Okay, in particular, this vertex has multiplicity 3, this vertex has multiplicity 7, and this vertex has multiplicity 13. So we know all of these dimensions. Sorry, I don't think I have this constraint for the KK tower. So I think we have only 2 constraints. No, we do have 3. Actually, we understood how to write the third constraint in that paper. We do have 3 constraints. Right. So we have 3 constraints, and we have 3, 7, and 13 variables. So not in general, you would expect not to be able to solve except in the 3 in this case. So we input. So all we do, we take the constraints that we have here, input J1s, and try to extract. Of course, in exactly what way I'll explain now. So
Sorry, quick question. When you were talking about the splitting just now in response to
Yes, these lines are splitting.
So these guys split.
Yes,
and then
yes, yes, yes. Oh, that's not the way. Yeah, there. Right. So apart from literally delta, so this vertex here, there are always more than 3 variables. But okay, let's actually just consider this case, but only 2 constraints. So let's take constraint f0 and f0j1. Now what we do is, so I have now 2 constraints and 3 variables, so I can solve for one in terms of the other 2, which is what I do here, right? I solve for f01 and f02, both in terms of f03. Okay, turns out f01 we get a solution, but f02 is equal to minus f03. Now immediately there is something that we can input here, which is the fact that we are in a unitary theory and these are OP coefficients, positive OP, non-negative OP coefficients, which means that both of these things should be greater than or equal to 0, which means they're 0, right? So immediately both of these get killed. And yeah, so this one extra stipulation actually turns out to be very powerful for us, because in both of the other cases also we have the same thing. In the case where we have 7, again we get some expression like this, where you have some OP coefficients in terms of others, where you have something is minus something, minus something, minus something, minus something, minus something, but then if all of them have to be non-negative, then all of them are 0. So in fact, in both of the cases where we have 7 and 13 OP coefficients, we are still able to solve just 3 constraints. And furthermore, we find a lot of zeros. So 3 out of 7 are non-zeros. That means the 4 OP coefficients there are 0. And 2 out of 13 are non-zero, so 11 are 0. So there is already, well, there's 2 takeaways from here. First is that indeed this is, so I think people who like numerical bootstrap say that numerical bootstrap is better than analytical bootstrap because you can always input unitarity, right, when you do numerical bootstrap. So this is a way where we can do that also when we do analysis. So that's the, but anyway, the point is that it looks quite powerful. The second thing is that we have these abundance of 0 OP coefficients, which is okay. It's not, so 0 is a strong statement, but the way you should interpret this is that as you go to stronger and stronger coupling, some OP coefficients are becoming subleading to some other OP coefficients, right? And all of these are OP coefficients corresponding to same string mass level, same spin, blah blah blah. Some are subleading to others. So it seems in your mind's eye you can think that okay, maybe there is some kind of, I don't know, emergent selection rule or something that can explain this. We don't know how to explain it yet, but indeed. So these are 2 takeaways from this. So that's one part. The other part of the other part of our analysis was the following. So yes, so to answer, I mean. So you can see the Reggie trajectories, I drew them split over here. So, so now what we want to do now, instead of going in the Kaluza client tower, we want to instead restrict to O2, 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 O2. But now what we wanted to do was we wanted to see if we can try to get the leading order OP coefficients for all states in a subleading trajectory. Now, this is a bit more dicey, like there are some assumptions, I will make clear what they are, that go into this. So we couldn't just fix it just with pure constraints plus integrability results. One, because there are many more variables now, and 2, because also the integrability data that we had at that point at least was not precise enough. So for these 2 reasons we had to make some assumptions. I'll explain them as well. But nevertheless, the procedure seems to be possible to undertake. Right. So yeah. So we restrict to O2, 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 and then we again consult our friends in Oxford. So they did this counting thing which I was explaining with this SO9s and your branching, blah blah blah. And what they noticed was the following. They noticed that it's true that the leading Reggie trajectory is non-degenerate, but the subleading Reggie trajectories, they are degenerate, but the degeneracy saturates at some point. So in particular, they noticed that if the mass, if you go on the subleading trajectories beyond some spin, basically you just have 4 distinct trajectories, rigid trajectories that you need to think about. So now it's actually possible to pose a problem to try to unmix this leading order OP coefficients on these 4 rigid trajectories. So that's what we tried to do. Again, here we have 3 constraints. So we have 3 constraints. In general, we have 4 OP coefficients, but we want to solve on a rigid trajectory. So this also means that we need to have some idea of how we expect these J's to move on a rigid trajectory. Now, for string theory reasons, based on 2D marginality, there was an assumption made in this paper that if you look at delta square, like the dimension square, as a function of the mass level. So the mass level and the spin are the same thing. Okay, they're essentially the same thing, at least in this idea. If you fix a rigid trajectory, mass level and spin are not the same thing, but they are both moving you on the trajectory. So if you fix, so if you fix, so based on so the assumption was the following, that is, if you translate in the mass level on a rigid trajectory, then the J1 should go like this, like a polynomial, as A delta square plus B delta plus C. So this is an assumption that we put in. So we assume that J1M goes like this. And then what we do is we actually go back to the QSC, compute J1Ms for, well, because we assume that it's a polynomial, we actually computed it only for 3 states with 3 different values of spin, and then we were able to fix those coefficients. But indeed, you can tell, why don't you compute the 4th one, and then you will actually be able to see if this thing holds or not. It's true, we should do it, we'll probably do it at some point. But the reason it's a bit, so in order to do this, actually what you need to do is when you try to solve the spectral problem of super Yang-Mills using QSC, basically what ends up happening is that to get to higher states, it gets harder and harder to initialize them in perturbation theory. So what you actually should do is take a state and analytically continue it in spin, and then and the QSC allows you to do that, allows you to actually just build a rigid trajectory in that way by analytic continue in spin. So we need to use those techniques and do it. It was, I guess, a bit annoying for us at that time to do it, but now we are more resolved to do it. So we will kind of, at least for some of the states, this should not be an assumption. That's all I'm trying to say. Like it's something.
There is a 4th state, but you are solving the problem assuming there.
No, I keep all 4 states. I'm just saying that I assume that all 4 states, as a function of the spin, they go like this. That's all.
So at the end, so can you unmute some of them?
We'll see. So the answer is not completely, but if we do some extra assumptions, yes. I mean, we can always unmix, but we can't fix everything unless we do some extra assumptions. Right.
Because I was thinking you have 3 constraints. So anyway.
Yeah. So I have 3 constraints. I have 4 states. In principle, I should know the dimension of all of these 4 states. I don't. I know the dimension of 2 of them very well and 2 of them not really. So I have more unknowns there. But then I also have unitarity, which gives me some inequalities. So yes, indeed, naively, you don't know what's going to happen. But if you see the Kaluza-Klein tower story, sometimes this non-negativity helps. So that was what we were thinking. Maybe it will help. So let's see how much it helps us. Right. So this is the assumption. So that's and so these were all of the assumptions that we had. And then this is another observation that we made, which we also used. So right. So the statement is the following. So if we actually look at this Chu plot here, you will see that there are 2 states which begin here, which at spin 0. Then at spin 2 there is a 3rd state which joins the game, and then at spin 4 there's a 4th state, and then it continues. Now you can ask the question again. It's so nice that Parijat gave the talk before me, because a lot of the questions were motivated there as well. Like, so you can ask the question, like, suppose I take this state and take it all the way here. In principle, I can analytically continue QSC and I can bring the state there and I'll have some value of the dimension. There will be some solution of the Q functions there. So there is some value of dimension that I'll get, but this is not a physical state. So what you do is you impose that the OP coefficient vanishes at that state. So if I have OP coefficient as a function of the mass level, I impose that that function of the mass level should have a 0 at this point. Same thing I can do here. I can do that here as well. So that's the first set of assumptions that we have zeros here. Then you can go further. You can analytically continue even further. So in principle, I can analytically continue this all the way to spin -2 because CFT data is expected to be analytic in spin up to spin -2. So I can in principle continue till -2, and then I will be able to impose that all 4 should vanish. But actually, it turns out that there is a subtle way in which basically, if you take one of the subleading Regge trajectories and then analytically continue them all the way to spin equals -2, what you can do is you can show that you can use spin reflection symmetry basically to tell you that this trajectory will actually map to the leading trajectory. Will actually map to the leading Regge trajectory as you go to spin equals -2. So what does that tell you? That tells you the following. That tells you that basically, and this you can also see at the level of constraints. If you take Fernando and Tobias's constraints for the subleading Regge trajectories and analytically continue them to this point, to delta equals 1, you will actually get back the constraints that they get on the leading trajectory. So that's one thing. The next thing that you see is that actually the value of J1 as a function of spin for the leading Regge trajectory and one of the states in the leading Regge trajectory is the same. So even that, when continued to mass level equals 1, will have the same value. So the constraint is same as Fernando's, the J1 is same as Fernando's, and therefore the solution is also the same as Fernando's in the sense that you get the same value of the OP coefficient as well. So using the spin reflection symmetry, you can add another constraint that one of the subleading trajectories can be continued to the leading trajectory. So that's another input that we given. So yeah, so to add to the list of constraints, these are also stuff that we add. And then
so just to understand, it's really like a counting game. So if you go back to the previous slide, the number of constraints is the number of zeros that you put here. So 1, 2, 3, 4, 5, 6 plus this extra reflection. It's literally that you're
yeah. Yeah. So, okay. So as I said, by explicitly constructing 3 states on 2 trajectories, on the 2 basic trajectories, we established that J11 and J12 are that. There are some functions, whatever. So the set of variables to solve for are these. We have 3 constraints plus unitarity plus analyticity in spin plus the assumption on form for J1. So only the thing in yellow is an assumption. Everything else, I mean, okay, to be fair, also asking the OP coefficients to be 0 is also an assumption, but more famous people than me do it, so I think I'm allowed also. But anyway, so these are the inputs, right? So this definitely is an assumption. Also, there's some assumptions from analyticity in spin as well. Right. So we solve now the system with no more extra assumptions. We get 7 possible cases. Now, I said that we don't have expressions for J13 and J14. Indeed, we don't have analytical expressions for them, but we do have independent QSC numerics for them. It's just not precise enough. So it's precise enough, I would say, to rule out something, but not precise enough to rule in something. Okay, so indeed, so we can check against these predictions against some numerical predictions for J13 and J14. That immediately rules out one case just because it predicts something which is definitely not even close to what we get from numerics. But anyway, so there are 7 possible cases. Interestingly, 4 of those cases gives the same prediction for J13, and the other 3 give different predictions. Um, Furthermore, and this is also interesting, is even at this point already, our procedure is already a bit predictive. It's predictive because what we can do is now we can produce at least expressions for at least the 3 highest powers of delta in the highest powers of spin for constraints of the form f0 j1 cubed, f0 j1 to the 4, blah, blah, blah. And these are constraints that you will see if you take Fernando and Tobias's procedure and apply it for the next curvature correction. So in some sense, already the third, I think 2 of the highest powers is trivially fixed, but the third power is something new. And that something new in principle can already be checked if someone motivates Tobias to do the next correction, for example, right? Or the other way, maybe their procedure can take this as an input as well. So, but it's predictive, right? Okay, yeah, okay, whatever I said is also on the slide. All right, okay. So now at this point, to reduce from 7 cases to less than 7 cases, we allow ourselves to go for some ad hoc assumptions. So what we do basically is we construct constraints of the form f0 times j1 to the whatever, j1 to the k, and we expand it at small spin. And then we see some patterns that we get in these constraints, and then we ask for some particular pattern to vanish. Okay, it's really pretty ad hoc in the sense that we just say, okay, this pattern is nice, this doesn't look as nice, so we don't want that to be there. And then we just see if this stipulation is consistent with if the stipulation is consistent with there is the 7 cases that I told you previously. So, okay, basically when we do that, we get the 7 cases comes down to 3 possible cases, and all of the freedom is fixed. So in the 7 cases that we had, there was a lot of free parameters. Now we have no more free parameters after doing this. And out of the 3 cases that we have, only 1 case, 2 cases are immediately ruled out by matching with numerics. The third case is not ruled out, but I wouldn't say that it is ruled in. The reason I say this is because as you would have seen from one of the tables a few slides ago, like the number of digits of matching that we get when we compute these J1s is usually like 6 or 8 digits. But here the prediction that I get matches so I get like so the formula will predict 55.33333, and what I will get is like 55.4 or something like this. So, it's not, I'm at least for the kind of precision that I am used to, it doesn't seem enough to rule in. Nevertheless, the kind of angle that we go for is more, it motivates something rather than it is a prediction. But nevertheless, so this is what we get. Interestingly, if you believe this, which I mean, it's up to you if you believe it or not, because we also, as I said, we did some ad hoc stuff, plus it doesn't really match perfectly the numerics. Then we get some predictions. The interesting thing I'd like for you to note would be that if this actually works out, then in addition to seeing that there are these Kaluza-Klein towers of states with vanishing OP coefficients, it's also one entire Reggie trajectory of states seem to have vanishing OP coefficient. So in some sense, you can think about it as some more evidence for maybe some emergent selection rule as well. Right. Okay, so that brings me to the end of what I wanted to say. As I was saying, so the subleading behavior of some OP coefficients suggests an emergent selection rule. Can you explain it using some kind of hidden symmetry? Can you repeat these hidden 10D symmetry arguments that were done for the cases of when you consider the amplitude but then double trace corrections? There is also need for more evidence of this. So obviously one way of getting more evidence is just doing better numerics. So that's one thing we need to do, but also maybe in other theories. So this almost entire this procedure can be also carried out in ABGM. So that's something we're working on. Again, at the can we compute, so these f0s should also be computable in just in flat space string theory. So just to have something to check with, can we compute, there are subtleties there, so it's not actually probably possible to do that, but nevertheless it's good to at least have a direction, thinking in that direction, thinking that way. And then lastly, can we use further these bridge trajectories? So bridge trajectory is this trajectory, is this thing I was telling you about, where if you take one rigid trajectory to some point, you can actually reflect and hit higher trajectories. Can we use that to get even more constraints? Okay, so that brings me to the end of what I wanted to say. Thank you very much for your attention.
Thanks, Julius. Questions?
Can you comment on not just this big zero, but on the zeros that appear for specific values of delta on this other trajectories that you have?
But these I impose, right?
Those are the ones you impose.
Yeah.
But there are some further weird zeros, right? These physical values.
Yeah. So this I don't have any comments about. Yeah, I don't know what to say about that. Yeah. These I impose.
Sure.
These I impose, yeah.
But this minus 33 over 35 is just some.
Yeah. It is what it is, I think. If it means something, it's good. If it doesn't mean something, my assumption was wrong, so it's okay.
Slightly unrelated question, but so when you mentioned the results on the sum over f's and deltas derived from one over connections of
Yes.
filtering amplitude in areas,
Yes.
expansions are larger.
Yes.
So how are those things computed? Those
Oh.
corrections?
Okay, so I can tell you what I understand, but Connor is an expert. He does this stuff in ADS3 as well, I think. So maybe Connor can comment something. But I think the way you do it is, so you can write so you can write some integral over a sphere to compute some punctured sphere to compute some amplitude, tree-level amplitude in string theory. So the kind of conjecture that they have is that if you want to compute higher radius corrections, you have similar sort of integral, but then you integrate against some ansatz that they make of some functions with some fixed number theoretic properties. So in particular, there is some single valuedness that they demand. So they make an ansatz out of single valued functions, and then do these integrals, and then using that's one input that they take in. And then they're able to fix curvature corrections, but I don't know. Do you have some?
That's quite different from I've been trying to understand that for a while.
Okay.
But are the corrections known to all others, or?
No, the curvature corrections. No, it's just the second order. That's all. I mean, for O2, 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 they just know the first two curvature corrections. So their paper is actually quite well written. Every time I read it, I understand it, and then now it's a few months since I read it, so it's gone again.
So if we have no other questions, so let's close this session for lunch.
Thanks.